Hello there, my name's Gary Sims and this is Gary Explains. Now, if you're in the market to buy a smartphone or a tablet or a laptop or a Chromebook, then it's probably important you understand the naming culture for ARM processors. Now, you may be familiar with Intel and AMD processors, but of course for smartphones and tablets particularly, but now also different Apple laptops and Chromebooks, you can buy them with ARM processors in. So what's an Arm Cortex-X 4? What's an Arm Cortex-A 55? What's an Arm Cortex-A 720? And then if you throw the microcontrollers in there, what's an Arm Cortex-M 0 Plus? There's a whole bunch of naming here that if you're not familiar with it, it can be a little confusing. So that's why I've created this guide, a guide to how you can understand all the different aspects of Arm processors and how they are named. So if you want to find out more, please let me explain. Okay, so let's start with my beginner's guide to ARM Cortex CPUs, from feature phones all the way up to supercomputers. So ARM CPUs can be found almost everywhere, from consumer electronics with an embedded microcontroller, from feature phones of the 1990s to the Android smartphones of today, even laptops and supercomputers. ARM CPUs are inescapable. Now, it all started back in 1990 when Advanced RISC Machines was spun out of Acorn Computers, of course the people responsible for the BBC Micro hit in the UK, and of course lots of other things, with a mission to create a new global microprocessor standard. By 2021, 200 billion chips had been shipped with ARM CPU cores. Can you just imagine that number? 200 billion chips with ARM CPU cores. As I said, they're everywhere, and 200 billion of them somewhere floating around this world, even out in space. This is amazing. Now, ARM no longer stands for Advanced RISC Machines, but the company ethos remains the same. And I will note this here. Yes, it is ARM, capital A, small r, small m, not ARM, all capitals. In 2017, the company rebranded. Officially, it is now ARM, all lowercase for the logo, and ARM with a capital A when used in text. I mention that now because I always get a comment by somebody who says, "Don't you know that ARM stands for Advanced RISC Machines?" Well, yes, I do. Okay. And here it is, the press release. Look at that. Advanced RISC Machines Limited, a new silicon company, has been formed in Cambridge, UK. And where are we today after all these years? Look at how it is dominating so many markets. So in this video, we'll look at the different ARM architectures, starting from ARM v6. There were others before that, but that's really kind of ancient history, really. Then we'll look at the Arm Cortex-M series, the A series, the X series. And that's one of the reasons why I'm making this video. They're all different. And it's important to know the differences, so this is kind of an explainer so we can just get a handle on all of that. I will mention in passing the Neoverse series and also ARM CPUs designed by other people, not by ARM. So over the years, the ARM instruction set architecture, ISA, instruction set architecture, has matured and developed. It was a 32-bit architecture and then it moved to 64-bit. That's with the exceptions of the microcontrollers. They are named ARM V and then a number, as we saw earlier, ARM V6 dash, and then either an M or an A for microcontroller or application. So you get ARM V6M, ARM V7M, ARM V8M. That's the microcontroller instruction sets. ARM V6, ARM V7A, ARM V8A, ARM V9A. Now notice often the A is dropped because we assume generally we're talking about the application processor, and only when we are specifically talking about the microcontroller do we make sure the M is on there. So you'll even hear me say this is an ARM V8 chip or an ARM V9 chip. What I mean is it's an application processor, not a microcontroller. If I was talking about microcontroller, I would put that M in there to make that difference. Now, talking of the microcontrollers, the ARM V6M microcontroller instruction set is the smallest supported by any ARM processor, numbering just 57 instructions. And ARM V7M for microcontroller added support for DSP extensions and for the floating point unit. And then ARM V8 adds support for trust zone. ARM V8M adds support for trust zone security extensions. And this is a brilliant diagram. This shows you some of the microcontrollers that are available from ARM. We'll talk about these in a minute. The M0 Plus, the M3, the M4 and so on. And it just shows you the greater range of instructions that are supported according to the particular architecture and the particular extension. So for example, if you've got a floating point unit, you're going to need some floating point instructions which have been added in there and so on. Now, what versions are there of the application ISA? Well, ARM v6, which was published in 2001, was used by the Arm 11 CPU cores. These cores are found in the original iPhone and in the Raspberry Pi 1 and the Raspberry Pi Zero. So you can still buy a Raspberry Pi Zero today, and inside of it is a processor that is using the Arm v6 architecture. It's still relevant today because people are writing compilers and software and so on that runs on the Arm v6 architecture. Then Arm v7 was the major 32-bit version of the Arm instruction set. It's often called ARCH32, Arm Architecture 32. It was used in Android smartphones until around 2015. It was used in iPhones until around 2013. And then we had Arm v8, which became the mainstream 64-bit version, so ARCH64, and it can optionally have a 32-bit mode so that it remains compatible with what was already out there. And now we're on Arm v9, the latest iteration, and it is 64-bit only. Now I do have videos here on this channel about Arm v9, specifically when it was announced, what it brings to the table, if that kind of thing interests you. Now, what do we have in the Cortex-M series? So Arm's 32-bit microcontroller CPU cores are optimized for power, efficiency, and deterministic operation. This is important when you are doing real-time embedded stuff. You want to be able to know that a certain amount of time will go past, or a maximum certain amount of time will go past before something else is guaranteed to happen. An interrupt is happening, things are returning from a certain place, because you don't want, like we've all had with our PCs, whether it's a Mac or whether it's a Linux or whatever, it kind of freezes for a second or two because it's doing something and it doesn't even get time to even, move the mouse on the screen. That's because it's not deterministic. It's off doing lots and lots of things. Microcontrollers are much more important than you can guarantee you know what's going to happen. Now, they run at much lower clock speed than other ARM CPUs, so some of them even as low as maybe 48 megahertz, 32 megahertz, maybe even up to 100, 150 megahertz, but certainly not up into the gigahertz range as we're used to with other ARM CPUs. And here's the big thing: they don't include a memory management unit. And that means they don't run traditional operating systems with virtual memory features because there is no MMU. So it doesn't run Windows, doesn't run Linux, doesn't run Android, doesn't run iOS, doesn't run Mac OS. However, there are lots of real-time operating systems out there. There is even a real-time operating system version of Linux that kind of gets shoehorned onto chips without a memory management unit. And there's even Piccolo OS, the operating system that I wrote and made videos about here on this channel, completely open source for the Raspberry Pi Pico. If you check that out in my GitHub repository and on my channel here for videos about all of that. So if you are interested in videos about MMUs and virtual memory, I also have videos about that here on this channel, so you can brush up your knowledge on those. Now, they're found in lots and lots of applications. This is just a fraction of them that we could mention. Blood pressure monitors, glucose monitors, lighting, smart metering, universal power supplies, POS terminals, simple touch interfaces, cameras, audio players, wireless headsets, of course the Arduino, the Raspberry Pi Pico. I mean, these microcontrollers are very cheap and they're low power, but yet they're clever enough and good enough that you could run a little display, touch display, and so they're great for all kinds of consumer electronics where you're not putting in a full-blown CPU for running, Linux or something like that. So here's a quick look at some of the microcontrollers that ARM has released. These are not in date order, but in name order. So the M0 Plus has the smallest footprint and lowest power requirements of all Cortex-M processors. Then you've got the Cortex-M3, one of my favourites personally, which is a general purpose and deterministic processor with hardware divide. I do have some videos here on this channel looking at the different power efficiencies of ARM Cortex microcontrollers, RISC-V microcontrollers, and ESP32 microcontrollers, and no surprise the fact that the ARM ones come out on top. You then got the M4, which has the option for a floating point unit and for some DSP stuff. The M7, the highest performing processor in the Cortex-M family. Those were all ARM v7-M, except for the first one. And then we had ARM v8 release, which included a whole bunch of stuff for security, because if you're doing things, fingerprints or PIN numbers or passwords, you don't want any of the software to be able to accidentally read that stuff. Cryptography keys. You'd rather that it was in its separate own area, trust zone that's called. Whole big topic, won't go into that now. But the Cortex M33, the M55, and there are others, are these ARM v8 microcontrollers. Now here's a quick thing. I don't expect you to go into that in too much detail, but as you can see, lots of no down the left hand side. This is the Cortex-M 0, and then as we go across, a lot of it becomes yes, optional, or these are the things you can add in. So basically, you improve the features as you go across the range, and that's of course like in any product really. The bigger, the better. The more expensive, of course, but of course you're maintaining that power efficiency and so on. Okay, moving on to the Cortex-A series. So this is what you've been finding in smartphones. So let's say, for example, here the Cortex-A8. That was released in 2005, but it was a while before it got picked up into smartphones. So in 2010, for example, we find it in the Apple A4 processor in the iPhone 4. The Cortex-A9 was found in the A5 processor in the iPhone 4S. Then you've got, for example, the A5, which was in the Snapdragon S4 Play. There are lots of other places these chips appear. I'm just giving you one example so you can kind of fix in your mind what we're talking about. And then we had the Cortex-A7 and the Cortex-A15. This was the first time that ARM released its big dot little setup. So you might have an octa-core with 4 A7 processors in it and 4 A15 processors in it, using that big dot little setup. So it uses power efficiency cores when it needs to, and only calls in the big guns, the big core, when it needs to, when it's playing a game or something like that. So that first came out in 2011, the chips. We kind of saw those around in sort of 2013. And then after that, we then get, so 2012, we then see the ARM V8, which is the 64-bit version, as I mentioned earlier. So the A53 and the A57 were released in 2012. They weren't immediately picked up by the smartphone companies. However, there's a whole history about that, which I've covered in other videos and other articles over on Android Authority. But when they did get picked up, again, it was in that big dot little format. So you might have 4 A53 cores and 4 A57 cores. And then you get the A72, and that was in 2015. Now, from this point onwards, as you saw in that previous slide, there was some gaps in the time when these processors were released. It wasn't always year on year. It wasn't always necessarily, the next thing. But once you get to the A72, then really ARM got themselves into a stride where every year there's a new processor with new performance gains, new technology, and that's been continuing on, and certainly recently, over the last few years, double-digit performance increases every single year. So this all started with the A72 back in 2015, a refined version of the A57, but you still paired it with an A53 in that big dot little setup. Then the A73, which focused on sustained performance, absolutely amazing chip, that they really did want to get it, that when you ran that CPU, not the GPU, but when you ran that CPU at full throttle the whole time, full power, it would not have to dip down to get cooler because it could maintain that sustained performance. Then we get the A55, so that replaced the A53, and the A75, and now we've been introduced to Dynamic, which replaces big dot little, allows for greater flexibility in pairing up different types of cores together. Then we've got the A76, which was a clean sheet microarchitecture design, starting from scratch, and that was a really good chip as well, and that got paired together with the A55. ARM doesn't necessarily bring out a new efficiency core every year, maybe not even 2 or every 3 years, but when it's needed, you get one. So we did have the A53, then we had the A55, and there was 5 years between them. Onto the A57, 20% in performance improvement, and that again was coupled with the A55. And then we got a big change with the A78, which we will talk about in a minute, which was the first year when it was no longer the big core, because you got the introduction of the X1. So you had the A55 and the X1 and the A78. And so what does that mean? Well, we used to have this 4+4 setup. So 4 Cortex-A53 or 4 Cortex-A55, and then 4 Cortex-A57 or A73, whatever you were doing, in a 4+4 setup. However, once we got the X1 coming in, then now that opened up to a much more flexible, and of course then there was Dynamic already laid the ground for this, so the traditional de facto standard becomes 1+3+4, so 1 X1 core. So just a quick refresher, I haven't talked about the X cores, we will do more in a minute, but they became the kind of the ultra performance cores. So you'd put in a big ultra performance core, and then you would not put in many of them necessarily because it was a bit more power hungry, but it did bring you the performance. So the de facto became this 1+3+4 setup. However, when the Google brought out the Tensor 1 and the Tensor 2, they had a 2 plus 2 plus 4, so 2x cores. That was very interesting. And then when the Google Tensor 3 came out, generation 3 came out, you had 1x core again, but then you had 4 of the A cores, the A whatever was being used, and then 4 of the power efficiency A cores. So there's 9 cores in that one. This all comes about because of dynamic allowed this greater flexibility, but it gets even stranger with the Snapdragon 8. The Gen 2, you had a 1 plus 2 plus 2 plus 3, and that was because these were both A cores, high performance A cores, but one of them had 32-bit support and one of them didn't. And then when you get the Gen 3, you get a 1 plus 3 plus 2 and only 2 power efficiency cores. So power efficiency cores went down from 4 to 3 to 2, and now with the Dimensity 9300, it's actually 4 X4 cores and 4 Cortex-A high performance cores and no power efficiency cores, the all big core CPU. So there we go. With dynamic and with the introduction of the X range, we get a much greater flexibility, and truly Google, Qualcomm, MediaTek, they've all taken that and tried different variations to create the chip that they wanted. So great flexibility there available to ARM's partners. So talking about the ARM V9 series now, we now have the Cortex-A 510 coupled with the A710. So that's the power efficiency core, 2021, new cores across the board with the X2, which we'll talk about in a second. The A715, same performance as the X1, if you clock it at the same clock speed and it has the same cache. So absolutely amazing. That was 2022. The X1 we saw in 2020. So just after 2 years, the big core had caught up with the very big core, or the ultra core. So that was an amazing chip. And now we've got the A720 with the A520. So again, a new power efficiency cores, new cores across the board with the X4. Of course, I've got videos about all of those here on this channel. And of course, there are accompanying articles over on the Android Authority website, many written by Robert Triggs, who knows what he is talking about. And as I said, here's the X core. So we had the first one in the 2020. So that tweaked A78. Then in 2021, 2022, 2023, we basically went up to ARM V9. So the X2 was truly divergent from the other A cores. And every year we've had a greater than 10% performance uplift when you're using the same clock, the same process node, the same caches. They've managed 10% improvement just by making the internals of the chip better, the microarchitecture, how it handles stuff. Forgetting the caches, forgetting the clock speed, forgetting that you're now down to 5 nanometers or 7 nanometers or 3 nanometers or whatever. This was just internal improvements. And then when you add on top changes in clock speed, changes in caching, changing in process node, then you get even greater performance increases. Okay, so let's just mention quickly, there is this Neoverse series. In 2018, ARM announced a server-specific product range called Neoverse. So servers, of course, have a different power budget. They're not running from a battery. They're not in your hand. They're in a big rack, in a server center, in a data center somewhere. And they need things like I/O, and 8 cores isn't going to knock it. We're going to need much more cores than that. You know, 16 cores, 32 cores, 128 cores. These are the kind of things that we need. So you've got the Neoverse V1 and the Neoverse V2, with the V2 being the ARM V9. You've got the Neoverse N1 and the N2, with the N2 being the ARM V9. And the difference in the V range and the N range, the V range gives you the best single-threaded performance, but you might not have as many cores because the cores are going to be slightly bigger. So it's kind of like the X1 and the X2 and the X3 kind of idea, but for servers. And then when you've got in the N range, they're still highly powerful cores, but not quite so big because you want lots of them. So you're going to want maybe 128 cores because you're running a server. So you're running a web server. So you want all of these kind of requests coming in. You want them dealt with rather than just one core that's particularly fast. So depending on what you want, ARM offer the different things here, and these have been picked up by Amazon, by Ampere, by lots of other companies, and they've built these. And so of course you can now get ARM servers from Oracle, from Google, from Microsoft, from Amazon. You can get an ARM instance running in the cloud. And the latest Microsoft chip that I mentioned in a previous video, that's also based on these Neoverse cores. Okay, so let's just close up with the fact that there are ARM chips designed by other people. So ARM have 2 types of licenses. They have a core license, which allows the partner to use the off-the-shelf, so the Cortex-A55 or the 520, the X1, whatever, and they can incorporate that in their processor. They might add in a GPU, they might add in an NPU, they might add in, you know, a DSP, an ISP, an image signal processor, whatever they're going to put in to make their smartphone chip, whatever they're going to do. But the CPU part is basically ARM license it to them, and they just say, right, we'll pop that in our chip here. But they also have a architectural license which allows for companies to design custom processors, nothing to do with ARM cores, custom processor. They start with their own engineers, they've got the specification, they've got the instruction set architecture, they know what they've got to build, but they can go ahead and build it. And of course ARM doesn't grant that many architectural licenses, though there have quite a few been done. Because custom processor cores can take years to design, you need an engineering team, it's great expense, and so on. And so you really have to want to do it. And so there are companies that have done it. For example, there is Apple that we mentioned here. Apple with their A series for the iPhone, starting with the A7. That was Apple's clean room design. Of course, you've got the M series for the Macs, the M1, the M2, the M3. You've got the Qualcomm Snapdragon X Elite, which has just been announced, and I've got several videos about that. Also, Samsung, Nvidia have done in the past, maybe do in the future, their own custom chips as well. And there are also several server companies that also have picked up architectural licenses. So an ARM chip that is not designed by ARM is allowed to be designed, but that last point here I didn't mention, processor design and an architecture need to pass a conformity test to ensure they are 100% compatible. So they're not divergent, going off, doing their own thing. They have to be able to run the same software that all the other ARM chips do, because it keeps the ecosystem coherent, keeps the ecosystem together. And that's why, in fact, at one point Samsung had an SoC that had some off-the-shelf ARM parts in it, CPUs, and their own custom-designed CPUs, and they, of course, they were all running the same apps, running the same operating system, doing the same things, because they had that 100% compatibility. Okay, that's it. If you've got any questions, please do feel free to ask me in the comments below. Okay, that's it. I'll see you in the next one.